Good morning, everyone. Welcome to chemistry class. I am going to be starting in your book on page 427 today. We went ahead and skipped over the experiment that was involving calibrating thermometers because I didn't think we need to do it. And plus, you're not here, so how boring would that be to watch me do it? But if you like, you can look up an experiment like that on YouTube, and if you'd like to see that, I can maybe look and find one if you want to watch it, but I have a feeling you probably don't. So anyway, today I do want to start with the little green section on page 427 that's talking about Lord Kelvin, William Thomson, first Baron Kelvin. He has a lot of names. And you can imagine what he was known for, since we do measure temperature with Kelvin. I really liked the little snippets about these scientists because a lot of them were strong Christians, which I just think is really cool. So he was a physicist and an engineer. His work was extremely important in the formulation of the first and second laws of thermodynamics. And as I mentioned yesterday, the first law of thermodynamics is probably one of the most important laws of chemistry and of science. So he was very smart. He's widely known for realizing there's a lower limit to temperature called absolute zero, and the unit that we know as Kelvin is named after him. Good morning. I am on page 427, and I'm just talking about Lord Kelvin, William Thomson, first Baron Kelvin, just because I think it's interesting to talk about the scientists mentioned in the book, because a lot of them that did groundbreaking research were strong Christians. So he was the one who figured out there was absolute zero, which we name after him. We name Kelvin after him. And he started all of his classes with prayer when he was a professor. And I really liked the quote that they gave at the very end of the green section from him that says, "Do not be afraid of being free thinkers. If you think strongly enough, you will be forced by science to the belief in God." I thought that was interesting because a lot of people now will try to say that God and science don't go hand in hand. And he was just saying, if you study it hard enough, if you think hard enough, you can't help but believe in God. So I thought that was cool. The Kelvin temperature scale is named after him. So just wanted to start off with that. And now we will move on to the calorie unit. We are going to start talking about measuring heat. Chemists sometimes use a unit other than joule for measuring heat, and it's known as the calorie. A calorie with a capital C is the amount of heat necessary to warm 1 gram of water 1 degree Celsius. The reason that they don't always measure in joules is because chemists didn't always know that heat was a form of energy, so they didn't know they could measure in joules. And I guess they just got used to using calories. So joules you'll more likely see when measuring heat, but sometimes they'll use calories. I'm moving on to page 428. So there is a relationship between the calorie and the joule. 1 calorie equals 4.184 joules, and we'll use that conversion quite a bit in some of our upcoming problems, so you'll need to highlight that. You can use it just like we've used conversion factors in the past. That is not an exact number, the 4.184, so you do need to think about the significant figures when you use that number. And calories should sound familiar because you've seen them on food nutrition labels. Now, those calories do have to do with the calories we're discussing, but they're not the exact same. When you eat food, one of the most important things food gives you is energy. Walking, running, breathing, sitting and reading a book, it all requires energy, and your body gets that energy from the food that you eat. But the food calorie here is a capital C, and that is not the same as the chemistry calorie. So sorry, I misspoke earlier. The chemistry calorie is a lowercase c. Food is a capital C. because 1 food calorie, which is capital C, is equal to 1,000 chemistry calories, lowercase c. You could technically call it a kilocalorie, but chemists don't like that term. So capital C is the larger one, lowercase c is the smaller one. And the average human body uses 2,500 food calories to do all of its work in a day. And that is enough energy to heat 2.5 million grams of water 1 degree Celsius. I thought that was an interesting fact. That is a lot of energy. So it's pretty amazing that God designed our bodies to use all that energy without overheating. All right, I'm moving on, page 429, to measuring heat. If we measure the temperature of an object and notice that it begins to rise, we can assume that the object is absorbing some heat. And the opposite is also true. So if we notice the temperature is decreasing, it tells us that that object is releasing or losing heat. So there is a way to measure how much heat is released or absorbed, and that you'll see in equation 12.1. Q equals M times C times delta T. The Q stands for what we're measuring, which is the amount of heat that's released or absorbed. M is the mass of the object. C is the specific heat of the object, which we'll talk about in a minute. And the delta T is the change in temperature. Remember, we talked last module about when you see that triangle, that delta symbol, that means change in. So they give you another equation there if you need it. 12.2, the change in temperature is equal to the final temperature minus the initial temperature. So if they say we're starting out at 25 degrees Celsius and we're ending at 30 degrees Celsius, your change in temperature would be 30 minus 25, which would be 5, would be your change in temperature. Then now let's move back to the specific heat capacity, the C. I'm going to turn the page to 430. It defines it up there for you, that symbol C, the amount of heat necessary to raise the temperature of 1 gram of a substance by 1 degree Celsius. So in other words, said my internet's unstable, but it seems to be okay. Specific heat tells us how easy it is to heat a substance. So if you were to put a metal plate on the burner of the stove and a wooden plate on the burner of the stove, which one would get hot faster?
Plate and metal plate. I don't know. Metal?
Yes, the metal. So that means that the metal has a lower specific heat than the wood. And every substance has their own specific heat. So there's a little table there, 12.1, that talks about the specific heats of common substances. You don't have to memorize it, but we will be using this table for some of our problems, so you might want to mark it. Notice that the units there, I guess we're going to talk about that in a minute. Okay, let's talk about the units later. So first, they want to just kind of show you how to use the table. So if we had 1 gram of gold and copper, and we added the same amount of heat to each, then the gold would have the higher temperature, because if you look at gold, its specific heat is 0.1260. The copper specific heat is 0.3851. So it requires less energy to heat gold than it does copper. So we're going to do a couple of examples, 12.1 and 12.2, to make sure we understand how to use that number. So if you will turn in your student book to 12.1. And it's going to ask you which substance takes less energy to heat up, gold or zinc? Without looking at the answer, what do you think?
Less?
Yes, which takes less energy?
Gold.
Gold. Yep, gold is the answer to 12.1. Good job. All right, and the second question, 12.2. A 5 gram piece of copper and a 5 gram piece of iron are placed side by side on a burner. After 3 minutes, the iron reaches a temperature of 100 degrees Celsius. Will the copper temperature be higher or lower than 100 degrees Celsius? So we're comparing copper and iron there. Which do you think would the copper have higher or lower temperature than the iron?
Lower.
That is not correct. So iron is harder to heat up than copper. So that means the copper would be hotter. So the temperature of the copper would actually be higher.
Oh. Wow.
It's worded weird. It tricked me too. So yeah, the copper would actually have a higher temperature than the iron since it's easier to heat up. Pretty easy. Now we're gonna move on and figure out how to use that equation that we learned a minute ago. I'm gonna be honest, this module has been difficult with the equations that they have, but I've been doing a lot of practicing, so hopefully I can help explain it to you guys in a way that's helpful. All right, so we're gonna talk about the units there for specific heat. You'll see it's joules per, it's joules divided by grams times degrees Celsius. So the units for heat, which is Q, that equation that we learned earlier, Q equals M times C times change in temperature, will either be calories or joules. The units for mass, that M that you use, will be something like grams, kilograms, milligrams, something like that. The units for temperature we've seen before, Fahrenheit, Celsius, or Kelvin. So depending on the equation and on what units they're using, that will change our units for C. So we select the correct unit based on whatever's going to get our final answer in joules. So the one over in the table, they're using grams and Celsius. So say they gave us a problem that involved one of the substances on that table. Since they're giving the specific heat with units, joules, grams, and Celsius, I have to make sure my mass is in grams and my temperature is in Celsius in order to use that specific heat, if that makes sense. Okay. So let's see. Say you had calories instead of joules, then instead the unit would be calories divided by grams times degrees Celsius. So it's just based on whatever they give you in the problem. Okay, so you're gonna have an energy unit in the numerator, a mass unit in the denominator, and a temperature unit in the denominator. So it'll be one of those options. All right, let's move on to example 12.1 so we can see how to use this. To cook an omelet, a 5 kilogram iron skillet, you see iron there, must be heated from room temperature, which is 25 degrees Celsius, to 150 degrees Celsius. How many joules of heat must be used to accomplish this? So we're using the equation that they gave us earlier, and we're using 12.1, the table right next on the page before this. Okay, so first we need our temperature in degrees Celsius, which we do have, and we need our mass in grams, which we have kilograms, because we're using the specific heat over there, which is using grams and Celsius. So first we have to convert to grams from kilograms. So that's what they do there. And then they get 5 times 10 to the 3rd grams. And then they change that to scientific notation for significant figures. And then they're just explaining that. And then you basically just plug everything into your equation. So if your equation is Q equals M times C times, I don't have a way to put delta. I'm just gonna put change in temperature. So you're just gonna plug everything in. So Q will be equal to that mass that we just converted from kilograms to grams times that specific heat for iron. So if you look at your table on page 430, it's 0.4521 times the change in temperature. So our final temperature was 150 and our starting temperature was 25, so we would subtract those. and get our final temperature. And then you're just going to put that in your calculator. Seems pretty easy right now, but it's going to get harder, I promise. And then once you do that, Q will equal 280,000 joules. All right. That's one example when you're given all the things that you need. And soon they're going to start making you figure some of that out. So the next example on page 432, I'm going to start there in bold. If a 305.4 gram mass of copper that is initially at 75 degrees Fahrenheit is given 1,234 joules of energy, what will its final temperature be? Okay, so we're solving this time for change in temperature, not for Q. So we are going to start with our original equation, figure out what we need to do. So to get change in temperature by itself, I'm going to divide by mass times C so that those cancel out. And I get the change in temperature by itself, and then I'm going to divide by that on the other side. So what you'll end up with is your change in temperature is equal to Q divided by mass times C. Okay, so this is your equation you're going to work with, and that's what they figured out right there at the top. Once you've figured that out, now we need to think about all of our units before we can plug everything in. So first, we notice they give us Fahrenheit, and we need Celsius because we're using the specific heat for copper on the previous page, which uses joules, grams, and Celsius. So we need to convert our temperature. So they give us initial temperature of 75 degrees Celsius, and we did learn an equation in a previous module of how to convert that. Celsius equals 5 divided by 9 times the temperature in Fahrenheit minus 32. So we're just going to plug that in. So we're going to plug in 75 for Fahrenheit minus 32. And once you do that, you will get 24 degrees Celsius. That's our initial temperature, not our change in temperature. All right, so moving on, now we're just going to plug everything in to figure that out. So I'm going to use this equation here. So change in temperature okay, so they tell me that the energy that was given was 1,234 joules. So I'm going to plug that in for Q. And then that is divided by the mass, which was 305.4 grams, times C, which I'm going to use that table on 430 for copper, 0.3851. Close your parentheses. And when we put that in the calculator, we will get the change in temperature is 10.49 degrees Celsius. And they are asking me for the final temperature. So now I need to use that equation. You'll see it on the very bottom of 432 that they gave me before, that the change in temperature is equal to, change in temperature is equal to the final temperature minus the initial temperature. So I'm just going to plug it in. So change in temperature equals the final temperature we don't know minus, I'm going to plug in my value for change in temperature, 10.49 minus my initial, which I figured out here was 24. And to solve for this, we're just going to add 24 to both sides. That will cancel. And then when you add it in your calculator, you will get 34 degrees Celsius. Now, you will have 34.49, but they're wanting two significant figures, which is why they rounded down. So that's how they got that. All right, we're going to do some on our own. 12.3. All right. 12.3. Put that at the top. Okay. So it says a 432 gram aluminum rod is heated to an unknown initial temperature. If while cooling down to a temperature of 24 degrees Celsius, the rod releases 612 joules of energy, what was its initial temperature? And then it gives you a hint. It says when an object loses energy, its Q is negative, which makes sense because it's not gaining energy, it's losing it. So it's going to be negative, like subtracting. And then we'll talk about more about that later on. Okay, so step one, I went ahead and wrote down for myself what C was going to be. That way I had it. So if you look at page 430, we're talking about aluminum. So C is going to be 0.9000. And that's joules divided by grams times degrees Celsius. So we know C. I'm going to go ahead and put my equation out there so I can solve for what I want. Okay, so this is my equation I'm using. They're asking me for the initial temperature. So I'm going to solve my equation for temperature like I did before. That's going to cancel if we divide by mass and C on that side, divide by mass and C on this side to get temperature by itself. So change in temperature is going to be equal to Q divided by mass times C. All right, now we need to use our, let's see, trying to see what I did. Okay, it looks like I solved for, let me look at what the book says because mine's all jumbled up. Okay. All right, so they just plugged it in from that point. And then, okay, so I just did it backwards. All right, so we're gonna go ahead and plug it in and see what we get. So change in temperature is equal to Q they gave me was 612 joules of energy, and remember it's negative because they lost energy, divided by the mass is 432 grams, and that's in the right unit, times the specific heat, which I went ahead and wrote down up here, 0.9000. You're just going to plug that in the calculator and you'll get negative 1.57 degrees Celsius. So then you're just going to plug it in your temperature equation. So your temperature equation is the change in temperature is equal to the final temperature minus the initial temperature. So the change in temperature was negative 1.57 equal to the final temperature was 24 degrees Celsius. They gave me that minus the initial, which is what I'm solving for. So we are going to add, no, we're gonna, subtract 24. Now I'll tell you what, we'll add the initial because it is negative, so that way we can get it positive. We'll add it to both sides. And then once we have that, we'll have negative 1.57 plus the initial equals 24 degrees Celsius. And then I'm just going to add the 1.57 to both sides. And that will give you an initial temperature of 25.6 degrees Celsius. And it should actually be yeah, they rounded because they want 3 significant figures. Okay, did that make sense? Garrett?
Yeah.
That makes sense?
It kind of cut out on that last part.
Okay.
I couldn't really hear what you're saying.
Okay, so I basically just solved for the change in temperature because that's what my equation gives me here. And then I just plugged it into the temperature equation to find the initial because I had the final and I had the change in temperature. So I just had to find the initial temperature. So I basically just got it by itself, which you can do that before you plug numbers in if that's easier. That might be what the book did. Okay, we're going to do another one. We're going to do 12.4 and then we'll be done for the day. So I'm going to clear this out. All right, 12.4 says if a 16-gram object requires 85 joules of heat to raise its temperature by 22 degrees Celsius, what is the specific heat of the object? Okay, so I'm going to use my original equation, Q equals M times C times change in temperature. And then I need to get it by, I need to solve for specific heat, so I need to get that by itself. So we're going to divide by mass, and that will cancel, times the change in temperature, and then that will cancel. And I have to do that on this side. So now my equation will be C equals Q divided by mass times change in temperature. All right, and then I'm basically just going to plug everything in. So I need to make sure the units are correct. They did give me joules, grams, and Celsius, and those are all good units for what I'm looking for. So we'll just plug numbers in. So C equals Q, they tell me, is 85 joules. And that's going to be divided by, in parentheses, 16.0 grams times, it says the heat raised its temperature 22 degrees. So I know that is the change in temperature. So then you just plug that in the calculator. And make sure that the whole numerator is in parentheses when you put it in the calculator. Tell me what you get.
0.2414. And then
Yeah.
it goes like 7. So it would be 0.24.
Yeah, we're going to round to 2 places since we have 2 significant figures in 85 and 22. So 0.24 would be the rounded answer. And your unit would be joules divided by grams times degrees Celsius. Pretty easy. That's it for today.
Okay.
All right. I guess I will see you tomorrow. Have a good day.